Okay, so I think I'd adopt a similar approach to thinking about evidence to a lot of the people who are involved in this workshop. And my approach here has been influenced by several of you. And I think one thing that is important about this shift is to shift away from focusing philosophical assessment on the initial acceptance of theories, although that's an important topic, where a lot of philosophy of science is focused on questions about the promise, feasibility, whether theories make novel predictions, and et cetera. And they tend to focus assessment on the moment when a new theory is introduced and how rational it is for a community to shift to using that new theory. I think it's valuable to look also, and in some sense, I think this gives us a better sense of how the evidence for our best theories is actually constituted by framing the question as a much more long-term question. And this is something that George has pursued and emphasized, and I've been particularly influenced by him in thinking of theories and evidence for them in these terms, namely that we should shift to thinking of the question, how stringently is a theory tested by subsequent research based on accepting it? And how can we be sure that in accepting a theory, especially one that involves a lot of new parameters or new degrees of freedom, that we aren't fooling ourselves, that the success in describing phenomena isn't somehow evidence of the flexibility of the new theory that we've introduced. So, and in shifting to long-term evaluation, I think one of the things that George has emphasized and several of you have also focused on is the consistency of independent measurements of fundamental constants as really an important source of powerful evidence for the theories we have. And so I'm going to be taking this approach and looking at contemporary cosmology and asking how successfully we can make a case for the current model of cosmology along these lines, and then very briefly indicating why I think there's some specific challenges that arise in cosmology that are interesting. So in brief outline, I'm going to first say something to introduce Lambda CDM, the contemporary model of cosmology. This will be very brief, I hope not too brief. And then I'll say a bit about one of the discrepancies that is being discussed right now, which is tension and different determinations of a particular parameter appearing in these cosmological models. It's not the only tension, but it's one that's achieved a lot of attention within the last decade or so. And then I want to say something more generally about the challenges that I think might be unique to cosmology. This is, again, something that for those of you who've studied other cases in detail, I'm really interested in considering how the case of cosmology compares to interlinking microphysical constants or other cases in other scientific fields. And then finally, I'll close with a few comments about how to think about realism based on the foregoing. So the Lambda CDM model is based on a really strikingly simple set of solutions to Einstein's field equations. These were discovered shortly after Einstein formulated the theory of general relativity by Friedman, Lemaitre, Robertson, and Walker, who each made different kinds of contributions. So they're often called the FLRW models for a shorthand. And these are strikingly simple. They are the most symmetric models that you could possibly have. And there's basically three different types of these models. The one that seems to be most relevant and is often just sort of taken now as the model that we base everything on is the middle model that's in Penrose's diagram there. That's a model where the space-time can be foliated into surfaces of constant time, and each of these surfaces has then a Euclidean geometry. So it's a very simple model in terms of the space-time geometry. Obviously, Einstein's theory allows much more complicated space-time geometries than this, but the flat FLRW model is strikingly simple. The other element, of course, is that there's evolution over time. They're expanding universe models, and there's a simple set of equations that govern what's called the scale factor, which characterizes how two objects nearby would drift apart if they were freely falling. So the scale factor just says how they will move apart or come together depending on the features of the model. And in the flat spacetime, the k equals 0 spacetime, as I said, the spatial sections are described by Euclidean geometry. I could say a lot more about those, but in the contemporary cosmology, then, you have this background assumption that the spacetime geometry is not exactly one of these models, but a perturbed version of one of these models. So you have to have some lumps and bumps over the simple uniform geometry that this describes. And this is often, so Martin Rees has a book, Just Six Numbers. The six numbers then characterize the features of these models. There's one set of numbers, the middle numbers here, that characterize the perturbations away from the flat space-time. So these are characterized in terms of how big they are, and a feature called the spectral index, which just characterizes their variation with length scale. And then, so those are the numbers that characterize, as I said, in the Lambda CDM model, we assume that it's a flat space-time geometry. So then we just characterize the perturbations away from that using these two numbers. There are other numbers that characterize what kind of stuff there is in the model. So these characterize the types of matter present and their densities. So these are, there's a customary way of writing these in terms of this density parameter omega, and then there'll be different numbers assigned for different types of matter, radiation, and the cosmological constant lambda. And finally, then there are a few other numbers that really describe things like the sort of describe more detailed features of the universe at specific epochs. So really within the last 50 years, cosmology is often described as having entered an era of precision cosmology, and that's almost entirely based on the prospect of using observations of the early universe in order to precisely constrain the 6 parameters I've described in the standard model. And so one of the reasons why this has been so important is that the early universe is thought to be physically very well understood. It can be described in terms of perturbations away from this basic model. The physics that describes, this is a picture of the CMB, the cosmic microwave background radiation. This consists of photons that come from the early universe to our telescopes. And the description of what happens that leaves this surface of photons is based on just sort of standard electromagnetic theory, nuclear physics, and plasma physics, nothing particularly worrisome. So as you go back to even earlier stages in the universe, obviously the physics gets more speculative. But one of the reasons why these observations have been so valuable is that the physical interpretation of them is actually relatively straightforward. So this is true for both the CMB and then other features like Bigbang nucleosynthesis. Again, this is an idea that in the early phase of the universe, there was a series of nuclear reactions where the reaction rates are controlled by the expansion rate in a simple model. And so if you describe the universe as consisting of a sea of particles, there'll be a very distinctive pattern of the abundances of these light elements that's sort of left over as the universe expands. And so what the diagram on the right illustrates is that for these light elements, the different curves represent their relative abundance. And then on the bottom, the x-axis represents the baryonic matter density. And you can see that the relative abundances are sensitive to the baryonic matter density. And then we can try to measure the primordial element abundances and find then what the baryonic matter density is at the stage at which nucleosynthesis occurred. So again, I'm describing this very, very quickly, but the overall idea is that given a description of nuclear physics in the early universe, which is not particularly controversial, it's not a really extreme environment from the standards of particle physics, we can constrain this cosmological parameter. One of the parameters I mentioned, what are the densities of different types of matter? Here, by looking at the primordial abundances of these elements, we can constrain the underlying parameter, namely how much baryonic matter was present at that stage of the universe. There's more detailed reasoning that takes the observations of the cosmic microwave background radiation as a starting point. But again, if you look at the peaks in the graph on the right, the shape of the peaks, their location, and their relative size also gives you constraints on things like the baryonic matter contributions and so on. So there's a lot of physics here, but the thing I want to emphasize is that these are the source of really precision constraints, high precision constraints on the cosmological parameters. And cosmologists are very happy that they're able to do this without having to worry about all the challenging astrophysics of figuring out local systems like galaxies and how they form, what their properties are. So this seems like a more direct way of getting constraints on the cosmological parameters. So here's a summary now of some of the values of these parameters. And so the first column really is just based on Planck data. So that's just based on observations of the cosmic microwave background radiation. So I showed you the image a few minutes ago. When you unpack all of the information that's contained in that data, using physical assumptions about the nature of recombination and so on, you can derive the constraints on the parameters listed here. So just for example, the first one is the baryonic matter density. So it's represented in a particular way, but that's essentially what the number is. And then the second one is the cold dark matter density. The third and the fifth characterize the spectra, how big the initial lumps and perturbations are, and then their other properties. And so these are all heavily constrained by the background radiation. And the second column, so this is from the particle data group, they show this just to show that adding other types of constraints doesn't change these numbers that much. So this is, the cosmologists are saying the Planck data themselves give us powerful constraints on these cosmological parameters, and we can add other information from other types of observations, but they don't actually shift the values that much. We'll see that there's a more interesting story to be told here about some of these values. And in particular, what's represented as H here is the Hubble parameter. And we'll see that the story isn't quite as clean if we look at other ways of determining H. And that's one of the sources of controversy, or one of the discrepancies that's currently driving a lot of work in this area. So that was meant to be a lightning tour. I don't know if it was too quick and dirty of the parameters in the Lambda CDM model, and giving you some sense of why cosmologists say that they're now able to do precision science using observations of the early universe to constrain these parameters. And I should say there's, in relation to the general theme of the conference, let me say two kind of side remarks about the cosmological perspective on constants. So I should probably throughout be using the word parameter here. There's only one of the terms that really could be called a constant in the way that we've been talking about universal constants, and that's the constant associated with lambda. All the others, I think, going back to Kareem's distinction, are more like constants of motion or parameters characterizing specific models rather than true constants. But there is a debate within cosmology about whether we should, in fact, take the parameters in these models. And all of these models are based on extrapolating local physics. So I haven't been emphasizing this, but in the description of the CMB and Bigbang nucleosynthesis, that's using physics that has all of the constants we've been talking about embedded in it. And there is a question that cosmologists have pursued at various points. Is it possible that in the very early universe, where physical conditions were different, that the constants varied? And sometimes people say this very specifically: do the constants vary with cosmic time? And so there's a great review article about this by Uzan from 2010, showing that there are actually very tight constraints that you can derive on this possible source of variation. And so I think really there are some theoretical challenges to this idea that we should apply kind of uniformitarianism in cosmology. The theoretical challenges go back to the advocates of the steady state theory. They thought it was unscientific to do anything other than assert that there's a principle that things have to be uniform. The principle they asserted was too strong. Smolin, for example, has recently argued that we should allow for the possibility of evolving laws, and he thinks that that might solve some theoretical challenges in cosmology. But really, from the point of view of observations, there's really no reason to introduce variation in the constants. There have been a few hints at various points. There were some exciting discussions about this as a result of some observations of quasars that seem to suggest that alpha might vary. But that hasn't really held up. So I think at the moment, the only reasons for considering constants varying with cosmic time are sort of theoretical considerations.
Sorry, Chris, I thought there was the lambda varying evidence is still, at least when I went to a physics conference last year, people still seem to be thinking about it as live.
So this is so the question of lambda, this is really whether it's a true constant or a dark energy. And if you think of it as something that mimics lambda, then you could imagine that it varies over time. And as far as I know, so I wasn't thinking of this because in that case, you're sort of replacing a true constant with a dynamical effect. And then it'd be pretty plausible for that dynamical effect to vary over time. And
so you think that's interesting. So you think that would be, in a sense, a different kind of story about a constant varying?
Yeah, no, that's actually a different story than what I'm imagining here. Here I'm imagining rather that the local laws can't be extrapolated appropriately to describe the entire universe, that somehow you've gone awry in doing that kind of extrapolation. And actually, I think I was going to mention this on the very next slide. So I'll skip to the second point here. As I was just saying in response to Kareem, cosmologists don't like constants, in fact. And so it's often the case that, so the only parameter that I've described that is in some sense a true constant is the cosmological constant, but cosmologists often try to replace that with a dynamical entity. And that's why they call it dark energy, which mimics a cosmological constant. But then you have some underlying dynamics. It seems like you have some physics behind it. There's a nice paper by Bianchi and Rovelli where they say that the title is Why All These Prejudices Against a Constant. And their argument is really, look, if you just treat this as a constant in the standard model, the observations determine a value of lambda. We should be happy with that. There are a lot of other reasons why physicists think that value of the constant is unnatural in a technical sense. But the other sort of thing that this reveals is that cosmologists don't take Nora's sensible shoes option. They always go for the high heels. They're always going for a possibility of novel physics, and they prefer that to just introducing a constant. And I should say the point I was going back to the first point on the slide, one thing that's really important to acknowledge about the Lambda CDM model is that from the very start, cosmologists have not been taking the sensible shoes option, right? If they did that, the FLRW models, what I mean by the sensible shoes option would be restrict the constituents of the universe to things that we have directly observed and characterized in other parts of physics, namely baryonic matter. If you restricted yourself to that, the FLRW models would in fact just be incompatible with observations. They would not fit with all of the things we've seen in cosmology. And the name Lambda CDM highlights that the cosmologists have introduced new parameters, lambda, and then new types of entities is how it's usually described, cold dark matter, in order to render the cosmological model compatible with observations. And so this question of whether to just stick with a more modest approach or novel physics, cosmologists have by and large already decided that novel physics is the way to go. And I'm not saying that this is unreasonable. And in fact, I think from a very plausible point of view, why would we think that we had been able to see all the relevant types of matter and energy on the Earth in our local environment? Whereas in cosmology, we're looking at enormous length scales and looking at different types of physical environments. So I don't think it's implausible, but this is the way that the cosmological modeling has gone. So let me shift now to just, again, really briefly saying, it's striking in looking at the way cosmologists then make the case for the Lambda CDM model, again, acknowledging that there is a case to be made given that they've introduced new parameters. And so Jim Peebles, this is just in his most recent book, but throughout his career, he's often emphasized a kind of what I think of as an overdetermination of parameters argument. And so in his recent book, he asked this question quite specifically: how can we judge whether this introduction of a non-zero cosmological constant is more than an adjustment of the theory to fit what is observed, as in a just so story? The answer must be to check for consistency with independent ways to constrain the parameters and otherwise test the theory without more adjustments. This became possible in abundance in the years around 2000. So he describes the years around 2000 to 2010 as a kind of revolution in cosmology because of the ability to give much more powerful independent constraints on these sorts of parameters. Now, his book is chock full of arguments that take this form. One example that he gives in this chapter right after the passage I quoted, he's looking at different ways of determining the matter density, the baryon density, and the primordial abundance of helium. And the thing that he's emphasizing here, so in the table, Z refers to redshift. So you can think of that as giving you an estimate of cosmic time, which is relevant to the measurements he's describing. So what he emphasizes in the discussion about this table is that you have measurements that are taking place at radically different cosmic times. So Z less than or equal to 0.1 is the local universe, to a cosmologist at least. And as you go to higher and higher Z, you're going out to higher and higher redshift. That means earlier and earlier cosmic times. So the high redshifts here will correspond to what I was mentioning earlier, the early universe tests. And what he's emphasizing here is that we have consistency of the parameter determinations through different epochs of redshift. And of course, what's tying together these quantities over those different redshifts is our background cosmological model, right? So if you ask, when you look at the CMB, or if you look at Big Bang nucleosynthesis and you determine a measurement of the matter density, why do you think that that's related in any way to matter density that you determine locally by looking at astrophysical tracers? Well, it's because you have described the evolution of the system using the cosmological model all the way from the early universe up until now. And so the fact that these are consistent determinations gives him great confidence that there's something correct about the background cosmological model. And he goes through and gives much more detailed versions of different aspects of this argument. So he has more detailed discussions of the matter density and the different ways of trying to determine that. So it's clear that at least for Peebles, and I think of, I mean, obviously he's well respected in the community, just having won the Nobel Prize, but this way of making the argument, I think, is quite powerful. And in some ways, I think, so with apologies to George, I'm going to paraphrase something he said about the solar system tests of Newtonian gravity. And I think we can pose the question about long-term evaluation of the Lambda CDM model in very similar terms. Namely, rather than thinking of, does Lambda CDM make predictions and so on, as some people tend to emphasize, we should instead ask or formulate the test question as whether calculated features of large-scale structure, expansion history, and other cosmological observables can be fit with a particular choice of parameters, but whether, so it's not that, but whether robust physical sources can be found for each systematic discrepancy between calculations and observations, with the demand that these increase, that we get closer agreement in a series of successive approximations. So again, this seems like an appropriate way to me of evaluating the success of the Lambda CDM models. But I think by contrast with the case that George describes in closing the loop, there's a few things that are quite striking. The first is just that the physical status of the best fit Lambda CDM model is at the outset unclear in several different ways. One thing is just that I said at the outset, we're using the simplest models that we could in terms of solutions to Einstein's field equations. why do we get away with this? Why do we get to use these highly symmetric models? So that's been a puzzle for a while. Some people think that inflation, the stage of evolution in the early universe, can resolve this problem. But in any case, there's a kind of model selection question. Why is it? Is there a physical reason for being able to use these particular models? And then there's also just the point that Peebles emphasizes, namely that adding lambda and cold dark matter automatically raises a physical question of what are these things? Do we understand the physics of these well enough, or are we just telling ourselves a just so story where we've introduced free parameters? So I think there's more of a challenge for the Lambda CDM model in assessing the starting point. I think it's also not as clear in this case what would count as a robust physical source. So again, does cold dark matter even qualify as a robust physical source for discrepancies? Again, I think most cosmologists would say, well, of course, what we've discovered is that there's cold dark matter. It explains a wide variety of properties. And so we can think of that as something we've discovered. We had a discrepancy. We discovered a new physical feature of the universe. But then the question is, and this is related to a point I'll be making in a moment, but the question is, what do you mean by robust? Do you have to have some non-gravitational or non-cosmological way of assessing these new terms, or is it sufficient to have a variety of cosmological evidence? And finally, there's just the complexity in assessing alleged discrepancies. So I want to move on to the Hubble trouble and very briefly explain an example that illustrates how difficult it is to even determine where the discrepancies are and what their implications are. So this is a diagram from a 2016 paper. I've quoted some results that are more recent, but the diagram itself is quite nice. So what this illustrates is that there's the authors take the gray bars to characterize their own results. So those are the results based on local observations. That's what's labeled R16. So this is, you've probably heard that in the late 90s, people were able to determine the local expansion rate of the universe with much higher precision due to the discovery of a new type of supernova and the use of them as standardizable candles. So this has led to a different way of determining the Hubble constant. And so the gray bars in the diagram represent the result of that series of measurements as of 2016. And so I'm calling this a local measurement. So it's used, it's based on these supernova results. And that's in effect looking at the local universe and seeing how things are expanding locally to determine the Hubble parameter using those methods. Now, the thing that's quite striking that I think this diagram illustrates very nicely is that this differs, and now the magnitude of difference is over 4 sigma. So it's well outside of the systematic errors that these different experiments report. It differs from the early universe measurements of the Hubble parameter. So in the early universe, this is an indirect measurement. It's not something that really can be directly measured, but there's indirect, once you fit the other parameters, that implies a value of the Hubble parameter. And it's quite a bit lower than the local measurements. And so this has been one of the, I mean, there are other discrepancies in the determination of cosmological parameters using different sources of evidence, but this is the one that has drawn the most attention recently. It's called the Hubble tension because it's a 4 sigma tension. And the thing that's striking is that it does seem to question whether we understand the connection between what's going on in the early universe and what's going on now. And really, that's what our cosmological model is meant to provide, a way of relating observations at radically different epochs of the universe. And so in this case, there are people pursuing, again, Nora's sensible shoes option. And I think this is actually probably, well, this is an important unresolved question right now. And I think that, I don't know if I have a systematic survey, but when I talk to cosmologists, a lot of them think that it is going to be ultimately resolved by systematics. There aren't a lot of cosmologists who are convinced that it's anything more than the difficulty of establishing the local distance ladder in order to take the supernova results and determine the Hubble parameter. And so in particular, Wendy Friedman and a group are trying to develop a completely different method to calibrate local distant measurements. And they seem to, those results right now lead to an answer that's sort of in between the measurements I reported on the recent slide. So I'm not going to go into the details, but it does seem like there's a possibility that's in effect a 0-point calibration. So in order to use the supernova to determine the Hubble constant, you need to have some local distance to the closest supernova, and then you're looking at supernova further out. But that 0-point calibration is really difficult. And that, if you have a systematic error there, that might actually wipe out the difference between the local and global measurements. That's a possibility that a lot of people are hoping for, that's really just a systematic effect. But this has generated an enormous amount of discussion. So I looked at a review article that was just published recently. Over 850 papers have been published on the Hubble tension. And so there's a huge variety of proposed solutions that would hope to resolve this tension. So let me now shift. So I'm not going to talk about these in detail, but let me shift to, I think, the challenges that this case and other cases in cosmology illustrate. And this is where I'm really interested to see how cosmology compares with the other kinds of cases that you all have worked on. So one issue is just one of quantity individuation. This is the kind of thing that Aaron has worried about in other contexts. But this is a question of what are the target quantities and what are the law-like relations connecting those target quantities to what we actually observe in particular measurements. And just to give you a sense of how this is relevant to, for example, the Hubble tension. So Estathiou has a paper where he argues that there's basically a confusion about this in some of the proposals regarding novel physics. So he argues that really, so if you try to modify the late time history of the universe just by changing how the Hubble parameter evolves, you're not actually going to be able to fix the Hubble tension, because the tension is really that the absolute magnitude, the brightness of the supernova is wrong. And so the proposals just don't get the target quantity right in some sense. So this is an interesting kind of case where you can see in the literature somebody saying, you've made this mistake. You're trying to fix the tension, but you're focusing on the wrong quantity. You haven't actually resolved the tension appropriately because of this confusion about what's being measured. So I think this is an interesting example of a kind of problem that philosophers thinking about measurement have really worried about. And I think more broadly, I'm interested in looking at Peebles' case more carefully and asking for his claims about how omega matter, how omega baryonic matter, and so on are related to one another. When you're looking at different redshifts, these are very different types of measurements. And so you have to have some argument to say why it is that looking at the parameter that appears in Big Bang nucleosynthesis is the same thing, the same physical quantity that is relevant for the much later measurements of matter distributions. So I think there's a really interesting set of questions here that are actually quite challenging. A second point, it really is a challenge in cosmology that we might not be able to have the degree of independence for the different types of measurements that we see in other areas of science. So in particular, all of these parameter determinations are based on the cosmological model, right? So there's a huge common assumption that these different parameter measurements have. So it's really hard to get the kind of independence that we see, for example, in looking at the measurements of the fine structure constant. There are some ways to try to get around this. So there are approaches called cosmography, or sometimes called model independent approaches, where you just try to do as much as you can without making specific assumptions about the dynamics. And there are some arguments of this form. I actually haven't looked into this in as much detail as I'd like. There are arguments of this form, but again, I think the question would be how far can you go? And what parameters can you really target with these kinds of direct arguments? And this would be a nice supplement for the model-based approach. There are also independent arguments that sort of support the basic assumptions of the framework. I can talk a little bit more about those if there's interest. I see that I'm already being long-winded, so I'll try to wrap up soon. So the last question then that I think is a challenge that's quite specific to cosmology is, again, we imagine that we have a target quantity that's connected in very abstract terms to the outputs of our observations. So what are the degrees of sensitivity to the idealizations that we make in drawing that connection? And so this is something that some of you heard about. I was talking about this in a paper at the Steinfest a few years ago. But for example, the FLRW models describe a universe that's completely homogeneous with a uniform distribution of matter. And we use perturbed FLRW models, so there's a bit of lumpiness. But the optical properties of a universe like that are very different than the optical properties of a universe more like what we actually see, which is clumps of matter with huge empty spaces in between. And so some people have been trying to assess, going back to the 60s, what happens if you actually model light rays going through an inhomogeneous matter distribution? How does that compare to the results that we standardly use from the FLRW models? So is it safe to treat the universe as if it has optical properties that definitely does not? How safe is that kind of modeling assumption? It turns out that there's a lot of arguments that it is actually fairly safe, but it's the kind of question that I think arises for a lot of the cosmological measurements. So you often sort of assume equations that you've derived from the FLRW models. How sensitive are they to the fact that especially the late universe is not well described by an FLRW model? It's much more interesting and has a much more complex geometry. Okay, so, so Teru and George have a very nice paper on molecular spectroscopy. So let me conclude by raising some issues about realism, which really resonate with some of the comments that they make in the paper. So let me just quote the end of this. This is a discussion of the molecular constants characterizing the rotational and vibrational modes of molecules. And they say, let me just read the quote, each time the molecule rotates, it has undergone on the order of 1,000 vibrations. And since the rotation constant depends on the distance between the nuclei, this must mean that the rotation constant that is being measured can only be a time averaged value. It does not correspond to any static or instantaneous state of the molecule. In other words, the molecular constants are a way of capturing a situation that is enormously more complicated, with time averaging smoothing or glossing over fluctuations of much shorter periods. And so similarly, I don't think, even based on the success of the Lambda CDM models, we can be realist in any straightforward sense about the FLRW space-time geometry. So similarly, although it's a very different physical system, obviously, but similarly to the point that Teru and George were making, the FLRW geometry is based on some complicated averaging over inhomogeneous distributions of matter at small scales, and there's no feature of the actual universe which the cosmological parameters directly represent because they're defined in terms of these background models. So what can we say, though, about the physical significance of these models? Well, I think it's very similar to what George and Teru say about the physical significance of the molecular models. They're physically significant because departures from them have been used to infer new physics and try to identify new features of the universe. So again, in cosmology, it's maybe, so I think the overall community accepts these inferences. It's not as secure as what was going on in molecular physics, but it is an inference that the cosmology community widely accepts. So in that sense, they're clearly granting physical significance in this sense to the FLRW models. So let me conclude then with hopefully a prompt to discussion. I don't know that Eric's here, but I'm going to adopt his terminology. So what do we say then about realism in light of these sorts of questions? So should we be what Eric characterized as a Pollyannish, naive realist, or I think defeatist is my word, or a defeatist, pessimistic coherentist? So I've been arguing that thinking about the measurement of fundamental constants really gives us a way of thinking about the successive theories that is much, that I think actually is far superior to just focusing on the considerations that lead people to accept theories. But to what extent does this support realism? I think there's also the possibility that there's just kind of a muddled middle ground. The middle ground is always for people who lack the commitment to advocate for one of the extreme positions. And as often I find myself perhaps occupying the muddled middle. And I was actually going to set up a poll, but I couldn't figure out how to do this for Zoom. So I was going to ask the participants to say where they fall, and I was going to give you the philosophers out, which is the simplistic one-dimensional parameter space cannot represent my subtle positions. Anyway, that was an attempt to prompt a bit of discussion to see where you all fall in terms of whether considerations in the cases that you know well, how they support different versions of realism. So I'll wrap up there, and I really look forward to the discussion.